Hello and welcome to Train Signal. You are watching Internet Protocols. In our previous lessons, we've spent a lot of time talking about the inner workings of Linux and how it interacts with system hardware. That discussion hasn't included networking, until now. Besides running as a standalone system, which it does quite well, Linux systems can also be part of a larger network. They can function as time servers, as we learned in our Linux system time and localization lesson, or it can serve as a database server, perhaps running the SQL Server software that we talked about in our Linux databases lesson. The point is, though, Linux boxes are easily configured to perform many functions in a networked environment. You usually only need to download the appropriate package. Networking is no simple task, though. In addition to the hardware, you must understand the concepts of protocols, ports, and addressing. Those of you coming from a Windows administration role will find many of the concepts familiar, and that's definitely a good thing. So in this lesson, we'll review basic networking and TCP/IP concepts. Then we'll talk about the different protocols. Next, we'll cover IP addressing and host names and how they're used to identify hosts on a network. And we'll wrap up with a look at ports and how programs use ports to facilitate network communications. Let's begin with networking and TCP/IP on the next slide. Before we talk about TCP/IP, let's review protocols. You probably already know that a protocol is like a set of rules and regulations, and these mandates determine how two systems communicate. Think of a protocol like a common computer language, one that each system, no matter how different, can understand. IP is the protocol used on the Internet, and combined with Transmission Control Protocol creates a network stack. And we'll talk more about that in just a moment. So we have a protocol that facilitates communications, but you also need hardware. Hardware components like network cards, or even some external devices, allow computers to communicate by facilitating data transfer. The most common type of network hardware is called Ethernet, which uses twisted pair cabling, where the pairs are twisted around each other in order to minimize interference. Ethernet is commonly referred to as a base T number, like 10 base T or 100 base T, where the number indicates the speed in megabits per second. Gigabit Ethernet at 1,000 megabits per second has become the recent standard. There are, of course, other types of network hardware. You have Token Ring, which was an IBM network type that's rarely seen today. Then you have Local Talk, which was used on early Macs, though most of those now probably use Ethernet as well. Then you have Fiber Distributed Data Interface, or FDDI, and also High Performance Parallel Interface, and others, which are high-speed type interfaces. These support even greater cable lengths than Ethernet. Wired networks aren't the only game in town. Wireless networks are almost always available today, whether it's in the home or the enterprise. Wireless networking types, or Wi-Fi, include 802.11, 802.11.b, then you have G, and even N. 802.11a and G have a maximum speed of 54 megabits per second. B is 11 megabits per second. And N, the newest standard, is up to 300 megabits per second. Not quite as fast as their wired counterparts, but still fast enough to get the job done. Okay, so now we have a protocol, and we have network hardware like Ethernet cards. The next thing you need is cabling, namely Category 5 or Cat5. And for Gigabit Ethernet, you've got the Cat5e or optical type cables. Ethernet also requires a hub or switch. You plug every computer into this central device, which in turn handles passing data between boxes. Switches are preferable because they send packets only to the intended computer, not to every single computer on the network like a hub. Switches are also full duplex, which allows for both parties to send data at the same time. Hubs, by contrast, are half duplex, so each computer must wait their turn before sending data. Certainly not the optimal situation for today's networks. Wi-Fi uses a wireless router that links both wireless and Ethernet devices, and also the Internet, usually via broadband. Data on the network is broken down into what's known as packets. And these are broken down into smaller chunks and sent a little at a time over the network, so if there's an error, the computer can just resend a smaller packet rather than the whole data stream. On the other end, the receiver holds the packets and reassembles them in the correct order to recreate the message. Ethernet packets are known as frames. This picture is deceptively simple though. The process of sending data is actually multi-layered and makes up what's called the protocol stack. Let's talk about the protocol stack a little more on the next slide. A protocol stack is software that encodes and sends data on a network so that the computer on the receiving end can interpret and reconstruct that data. The diagram on your screen represents the protocol stack. At the top, you have client programs that are at the application layer, and they initiate data transfers. The requests go through the transport, internet, and link layers on the client machine, where they leave and pass to the server, which processes the data in reverse. The server program runs at the application layer and replies to the client, which goes down the server stack, across the network, and back up the client stack. And you can imagine this happening many times back and forth with packets or frames. The hardware used at each layer can be different, as well as the operating system, as long as the stacks function the same. Other protocol stacks include NetBEUI, the original IBM and Microsoft protocol stack for Windows. Then you've got AppleTalk, which was for Apple, and Internet Packet Exchange / Sequence Packet Exchange, or IPX/SPX, which is a Novell stack. Most of these aren't very widely used anymore. Linux has support for AppleTalk and IPX/SPX. There are several protocols which can be classified as falling into one of the 4 layers of the TCP/IP stack that we saw on the previous slide. The 2 most important are the Internet and the transport layer protocols. These include Internet Protocol, or IP, and from the diagram we know that IP is a network layer or a layer 2 protocol. IP provides what's called a best effort method for transferring packets between computers. So what that means is the transfer isn't guaranteed. The data may come out corrupted or even out of order. IP is also the portion associated with the IP address. Then you have Internet Control Message Protocol, or ICMP, which is often used to send error messages. ICMP works by modifying the packet and returning it to the sender. This makes it an Internet Layer Protocol. User Datagram Protocol, or UDP, is a Layer 3 protocol, and it's a fast one, but that's because there are no delivery guarantees. Domain Name System and Network File System are built on UDP. And finally, we have Transmission Control Protocol, better known as TCP, which is the most widely used protocol because it has error checking and correction included. It does have a tiny performance penalty because of all that extra work that it has to do, but this isn't something that you'll notice. SMTP, HTTP, and FTP are all built on TCP. Like your home, your computer needs an address in order for another system to communicate with it. Network or IP addresses are used for this purpose, and each network host must have a unique IP, but the number can be changed at any time. So when a frame leaves a computer, it is usually addressed to another computer. 3 types of addresses are most important. First, we have the hardware address, which is also called Media Access Control, or the MAC address. The hardware address is 6 byte long, and it's a hex number separated by colons. To find the MAC address of your Ethernet card, you use the command ifconfig or ifconfig. You'd simply type in ifconfig space ETHN, where N is the number of the interface, usually 0 for the first card, 1 for the second, and so on. The line on your screen is a sample output and includes the interface number followed by the hardware address. The next most important network address is the IP address, and now it comes in 2 flavors. You have IP version 4 and IP version 6, the newer version. IP version 4 numbers are 4 bytes long or 16 bits. Address Resolution Protocol, or ARP, converts between IP addresses and MAC addresses. IP version 4 addresses are 4 10-base team numbers between 0 and 255, and each bit is called an octet. The sample IP address on your screen, 192.168.1.1, is typical. And again, each bit is called an octet. So 192 is an octet, 168 is an octet, and same for 1 and 1. IP version 6 addresses are 16 bytes long. This upgrade to IP version 4 includes more addresses and improved security. It uses Neighbor Discovery Protocol, or NDP, to do the conversion that ARP does for IP version 4. IPv6 numbers are represented by 8 groups of 4-digit hexadecimal numbers. Let's open a terminal window and try the ifconfig command. From the Applications menu, click on System Tools and Terminal. Now I know that I only have one Ethernet card in my computer, so I'm going to type in ifconfig space ETH, and I'm going to use 0, and that's for the first device. And again, you could use 1, 2, 3, and so on for additional devices that you may have installed in your system or server. And let's hit enter. And from the output here, again, we have the name of the interface, ETH0, and we've got the hardware or the MAC address here. Got some other information, network mask and broadcast information that we'll talk about in just a moment. Got some packet information as well, collisions, etc. Okay, let's go back to the presentation and continue this discussion on the next slide. Continuing our discussion on IP addressing, in addition to the IP address, you also need what's called a subnet mask. Now the IP address is divided into 2 parts. First you have the network address, and it's followed by the node address. Now each system on the same network segment must have the same numbers in the network portion of their address. And they must also have a unique node portion. So the subnet mask identifies the portion of the IP address that is a network address and the part that is the computer's address. They use the format of binary 1 for network and 0 for the computer, or 255 or 0 values. And again, 255 is the network and 0 is the computer. So when you see 255, that indicates that portion of the IP is used for the network address. As an example, a subnet mask of 255.255.255.0 says the first 3 octets represent a network and the last a node. Subnet masks can also be represented by a number of network bits in the address. For example, 192.168.1.1/24 has a network mask of 255.255.255.0, which in turn shows the network portion is 3 8-bit bytes, or the 24 that you see there following the slash. Continuing our discussion, IP addresses are divided into 5 different classes, each with its own default subnet mask. You should be familiar with each class and its net mask address range for the Linux Plus certification exam. Broadcasts are used to send a transmission to all computers on the network. It uses binary 1 values in all machine bits of the IP address, and the network portion may be set to the network's regular value. Taking a look at classless interdomain routing form, or CIDR, the first class is A, which has an address range of 1.0.0.0 to 127.255.255.255. And it has a reserved address range of 10.0.0.0 to 10.255.255.255. Next we have Class B, which picks up where Class A leaves off and starts at 128.0.0.0, and it goes all the way to 191.255.255.255. Its reserved address range is 172.16.0.0 to 172.31.255.255. Hoping these numbers aren't starting to all run together at this point. But next we have Class C, which starts at 192.0.0.0 and goes all the way to 223.255.255.255. Its reserved address range is 192.168.0.0 to 192.168.255.255. Next we have Class D, and its address range is 224.0.0.0 to 239.255.255.255, and it has no reserved address range. And lastly, we have Class E with the range of 240.0.0.0 and goes to 255.255.255.255 and also has no reserved address. The last, but certainly not the least important address on the network is the host name. This is simply the name of a computer and has two parts, the machine name and the domain name. And TCP/IP can link computer names to their IP addresses. Domains represent a collection of computers, and at the top you have .com or perhaps .edu, and then there are organizations under that, for example like Linux.com, and there can be further subdomains below that. Domain Name System, or DNS, is used to resolve or convert between IP addresses and their host names. But to do a manual DNS lookup, you can use the NSLOOKUP command, though this is officially deprecated. Its replacement is host. Then you have dig, which does a more complex lookup, and finally whois, which provides more general domain information. You may also want to use the -H option, which omits some of the legal disclaimers that might pop up, and they can be quite lengthy. Let's go back to our terminal window and try out a DNS lookup. Okay, first let's clear our screen with the clear command. Now let's try out the host command first. We'll type in host space, and I'm going to try linux.com and hit enter. And you can see it comes back with information about the IP address and some SMTP mail information. Now let's try dig, which is supposed to be more complex. We'll type in dig space, and we'll use the same address, linux.com, and hit enter. Let's scroll up to the top of the output. We have some header information here. We've got a question and answer section. We've got the IP address and the host name. And we've got an authority section here, followed by some additional information, and it ends with the query time, the server, when, and the message size. Now let's try the last command, whois. We'll type in whois space linux.com and hit enter. Let's scroll up again. Got some general information here, some description. We've got the listed registrant. We've got technical contact information. And we've got the domain servers. Okay, let's go back to our presentation and continue our discussion on host names. There may be times when you don't need a full-blown DNS server. For example, if you have a pretty small network. In those cases, you can use the etc hosts file, which holds mappings of IP addresses to host names. Now this file is purely local, so any change that you make in the file will only apply to that computer. And if you want the change to span the entire network, then you'll have to make the same update on each computer on the network. Normally, the Linux system looks at etc hosts before it takes a look at DNS, but you can modify this behavior by editing the file etc nsswitch.conf. You'll have to modify the host line, which reads IP followed by the host name. And finally, the etc networks file is similar to etc hosts, but it's for network addresses. And the format in this file is reversed. You have the name followed by the IP. Now let's go back to the terminal and take a look at our host file. And let's type in cat to display the contents of a file, etc hosts, and hit enter. And we only have a couple entries, and we have the IP address on the left hand side here, and then you've got the host name on the right. You'll also have some comments sometimes that indicate what the setting means. So we have IP address here 127.0.0.1, and that's assigned to localhost, and localhost.local domain. Now let's take a look at the networks file. Let's type in cat space etc networks and hit enter. Again, we have the reverse order for the network addresses. We have the host name followed by the IP. So for example, we've got loopback as the host name and the IP 127.0.0.0. Okay, let's head back to the presentation and talk next about network ports. We know how the network contacts a computer, but we also need to know how to contact a program. Network ports let you send your request to a specific program. These ports are assigned to programs at startup. This table highlights the most common ports and their applications, and it stretches over the next several slides. This is information that you'll absolutely need to memorize for the Linux Plus certification exam. So we'll walk through each port by number, the transfer protocol it uses, its purpose, and the types of servers that may use this port. First we have port 20, which uses the TCP transfer protocol. Its purpose is for FTP data, and an example server is Pro FTPD or VS FTPD. Port 21 is exactly the same. Then we have port 22, which uses TCP. Its purpose is for secure shell, and example servers are the OpenSSH server and Dropbear. Next we have port 23, which also uses TCP, and its purpose is Telnet. And an example server is in.telnetd. Then we have 25, which is another TCP protocol. Its purpose is SMTP, and an example server are the ones that we covered in our email and printing lesson: SendMail, Postfix, Exim, and Qmail. Continuing our review of network ports, next up is port 53, which uses both TCP and UDP transfer protocols. Its purpose is DNS, or Domain Name System, and an example server is Bind or DJB DNS. Next, port 67 uses UDP, and its purpose is Dynamic Host Configuration Protocol or DHCP. Example servers are ISC and DHCP. The next one you should recognize, port 80, which uses TCP, and its purpose is Hypertext Transfer Protocol, or as we all know it, HTTP. Example servers are Apache, Roxen, and THTTPD. The next one we should also recognize, which is 110, and uses TCP, and port 110 uses POP3. Example servers are Dovecot, QPopper, and POP-A3D. Our port review continues with 111, which uses TCP and UDP. Its purpose is Port Mapper. Example servers are NFS, NIS, and RPC services. Next we have 113, which also uses TCP. Its purpose is auth/ident, IDENT, and the example server is identd. Next up we have port 119, which uses the TCP transfer protocol. Its purpose is Network News Transfer Protocol, or NTTP, and example servers are Internet News, or INN. Then you've got Diablo and LeafNode. Port 139 uses TCP as well, and its purpose is NetBIOS, which is a window sharing program. An example server is Samba. Next is another recognizable one, which is 143, and uses TCP, and its purpose is IMAP. Example servers are Dovecot, Cyrus IMAP, and UW IMAP. Our network port review continues with 161, which uses the UDP protocol, and its purpose is SNMP, or Simple Network Management Protocol, and example server is Net SNMP. Next we have port 177, which also uses UDP. Its purpose is XDMCP. Example servers are the display managers that we learned about in our display manager lesson, and they're XDM, KDM, and GDM. Next there's port 389, which uses TCP. Its purpose is LDAP, and an example server is OpenLDAP. The next port, 443, uses TCP as well, and its purpose is HTTP over SSL or HTTPS. Example servers are Apache and Roxen. The next port is 445, which also uses TCP, and its purpose is Microsoft Directory Services, and an example server is again Samba. 465 uses TCP, and its purpose is SMTP over SSL or URL Rendezvous Directory. Example servers again are SendMail, Postfix, Exum, Qmail, or network routers. The list of ports rounds out with 631, which uses the TCP transfer protocol. Its purpose is Internet Printing Protocol, and an example server is CUPS that we learned about in our email and printing lesson. Next we have 993, which also uses TCP, and its purpose is IMAP over SSL. Example servers are Dovecot, Cyrus IMAP, and UW IMAP. Port 995 uses TCP/IP, and its purpose is POP3 over SSL, and it has the same example servers as 993. Next we have 5900 Plus, which uses TCP, and its purpose is Remote Frame Buffer. Example servers are VNC, and also OpenVNC and TightVNC. And finally we have ports in the range of 6000 to 6007, which use TCP, and their purpose is the X Windows system, and the example servers are x.org-x11 and xfree86, the servers that we learned about in the X11 installation and configuration lesson. It should be noted that ports below 1024 are called privileged ports, and access to these ports is restricted to root. This was a built-in security measure intended to ensure these services were trusted. The unprivileged ports are those greater than 1024, and they're open to all users. Most of the time you won't have to change these ports, but if you do, you'd edit the etc services file, which maps port numbers to names. Let's go back to the terminal and take a quick look at this file. I'm going to go ahead and clear the window. Then I'm going to type in cat space etc services and hit enter. And we have a pretty long list. In the first column here, you have a server name, then you have the port number and the transport protocol, and then you typically have some comments over here that describe things. Let's scroll up to take a look at this list a little closer. This goes all the way to the top. And again, if you wanted to edit this file and add in some new port mappings, you can open it up in your Vi editor. Okay, let's head back to the presentation. And that concludes our lesson on Internet protocols. Let's review what we've learned on the next slide. In this lesson, we covered Linux networking and TCP/IP. On the hardware end, we learned that Ethernet is the most common network interface and that TCP/IP is the protocol you'll most likely use. We then reviewed the different types of TCP/IP protocols. Next, we talked about IP addresses and how they're used in conjunction with host names to identify computers on a network. We wrapped up with a look at network ports and how they are assigned to specific programs. Thanks for watching, and I'll see you in the next lesson.